Can you see it? So for the first part, you're asked about RE prime and RE double prime. The really important part here, and where most of the marks are, is for drawing the MO diagrams. So draw two MO diagrams, one for the grounded state, one for the excited state, and that will actually help you answer the question, right? So the best answers to the long questions will include a diagram of some description. A picture speaks 1,000 words. So you've got RE prime greater than RE double prime. So actually I can just draw, can't I? So in your excited state, you've promoted from a pi star to a sigma star. Then all of these are full. It's a bit rough, but do any of you have any thoughts about why that might increase your bond length? Well, you've got the same number of electrons, so maybe think instead about the strength of the bond. What do you know about the strength of pi bonds as you go down the periodic table? Carbon-carbon double bonds are everywhere. What about silicon-silicon? Yeah, exactly. So as you go down the periodic table, they get a lot weaker. Sorry, I've just lost my mouse for some reason. 2 seconds. Let's try this again. Yeah, exactly. So as you go down the periodic table, you get less and less electron-electron overlap, especially for pi orbitals. Oh, I've lost all my annotations. That's a shame. And I've still lost my mouse. That's annoying. PowerPoint. So you've gone from what was effectively quite a weakly antibonding orbital because of the overlap to, oh, you can't see a thing, can you? There you go. Am I back?
Yeah, you're good.
So you've gone from a weakly antibonding pi orbital to a strongly antibonding sigma orbital. What's that going to do to your bond strength? Yeah, exactly. So you've got a weaker bond and less attraction. So the repulsion pushes the atoms further apart in a way. So the next one is about radii. So before we go any further, I need you to quickly define for me what is the radius of an atom? But you get these, let's do a radial distribution function as a function of distance. Have a peak and then they decay away, but they never get to 0. It's asymptotic. So what is the radius?
Like the furthest distance, you're like most likely to find an electron.
Yeah, so there's a couple of different definitions of varying degrees of applicability to different situations. So normally when you see those MO diagrams that you plotted in WebMO, those orbitals are normally plotted at 95%. So when all of this is 95%, and then this is the distance that's plotted. But for molecules, we can measure distances. So for example, this down here is the crystal structure of iodine. where you've got clearly defined two different distances between the nuclei. You've got a short distance, the covalent radius, and a long distance for the van der Waals radius of attraction between the two. The inter is y and the intra is x. And you can measure the distance between those nuclei, even though we have effectively got an infinite radius. So why do you think the covalent radius is less than the van der Waals radius? Yeah, exactly. You've got a bond. So the shared pair of electrons sort of pulls the nuclei together, whereas between molecules, you don't share pairs of electrons. But you get fairly weak intermolecular forces. The attractive forces are quite low relative to the repulsive ones. The iodide atom is slightly different. So people often try and make arguments here about how the lithium ion in Li increases the ionic radius that you can measure. It turns out that for lithium iodide, the lithium ion is so small it effectively fits in pockets between iodide atoms, and iodide is quite larger than iodine atoms in the gas phase. So why is an iodide ion larger than an iodine atom? What have you added? And if you have more electrons, what's going to happen to the electron-electron repulsion? Well, there's a step in between increasing electron-electron repulsion and the radius getting bigger. Do you guys remember the concept of Z effective, or effective nuclear charge? So that is the attractive force of the nucleus felt by an electron, and that includes the electron-electron repulsion. So if you increase electron-electron repulsion, you decrease the effective nuclear charge, and that's what increases. That's what expands the electron cloud. Okay, I think that's all we've got time for. The other questions aren't as long, so we've gone through the long ones. Just remember, for the long answer questions, you really are expected to say why things are happening. If you just give me the order of the bond lengths, that doesn't score you any credit. You need to tell me why. And the best answers will always include a diagram.
Thank you very much. Been helpful. Thank you.
Thank you.
Hi guys.
Thank you.